Hello, my name is Roberta Wilkinson. I'm a PhD student at the University of Oxford, and today I'm presenting our study of the active faulting around Dushanbe, the capital city of Tajikistan. Dushanbe sits at the northern edge of the Tajik Basin, a sedimentary basin which is bounded by the Pamir, the Tian Shan, and the Afghan platform. A set of north-south folds sweep up the basin interior, curving to the east at the northern boundary where they merge into the right lateral iliac fault, which runs through the south of the city of Dushanbe. There is a cluster of recent seismicity here in the central section, but much of the fault remains quiet. The magnitude 5.5 ISTerre earthquake occurred in 1989 close to the western end of the fault, although we don't know which specific fault it ruptured and there's no focal mechanism available. The area is very prone to landsliding, and as such, even small earthquakes can be dangerous, so we'd like to better understand the sources of seismic hazard around the city. GPS measurements suggest 8 to 15 mm per year of right lateral strike slip on the iliac fault, and on the order of 5 mm per year of shortening. But the GPS points are sparse, and they cannot tell us if the fault is locked or creeping. So we performed time series InSAR to measure the current deformation around Dushanbe. We processed Sentinel-1 acquisitions over the Tajik Basin using the NSBAS processing chain. Here are the Interferogram Networks. We removed 12 and 24-day interferograms to mitigate some of the bias associated with short-period interferograms. To aid unwrapping, we performed empirical corrections which we then added back in after unwrapping. The unwrapping path starts in the regions with the highest coherence, and this also helps us to unwrap successfully. We then perform an atmospheric correction using ECMWF's era weather models, and then we do a time series inversion. Here are the resulting velocity maps for the whole of the Tajik Basin. These bright red patches are agricultural areas which appear to be moving away from the satellite and are particularly prominent in the descending track. We interpret this apparent subsidence as a combination of groundwater extraction and phase bias issues. We try to mask out the subsiding fields using the RMS of the time series without losing too much of the descending data. There is a lot to talk about here, but for this presentation I'm going to focus on Dushanbe. Here are the zoomed in velocity maps, and we can see the trace of the iliac fault picked out very clearly by this colour change. We also see a sharp colour change on the Babatag thrust, which lies at the base of one of the basin's anticlines. We interpret this as shallow aseismic slip. You might also have noticed that the descending track is much noisier. This could be because the descending data is acquired in the morning when there's lots of mixing in the troposphere, or it could be something else like the differences between the networks. We're still investigating this. But now focusing on the east-west portion of the iliac fault. Profiles through the eastern section show a sharp step in velocity across the fault, indicating that the fault is creeping to very shallow depths. Looking at the ascending track in plan view, you can see that this sharp step becomes a smoother signal at the fault's western end. And here you can see this smoother signal in a western profile. When we compare our results to recent local seismicity, we see this cluster of earthquakes corresponds to the transition between the shallow creep in the east and the locking to the west. There is no recent seismicity along this locked section, so the strain is likely accumulating here and it probably poses some significant future hazard. We estimate a strike slip rate of roughly 8.5 mm per year for the fault, but we'll be modelling this in more detail to get more precise numbers. There are also outstanding questions as to whether our surface measurements reflect the deformation of the basement rocks, or whether the basin's sedimentary cover is decoupled from what's going on at depth. I will also briefly mention that we've been combining our InSAR work with analysis of Pleiades-derived digital elevation models. These tell us about the accumulated deformation. This is ongoing work, but we've been able to map out the structures associated with the iliac fault zone. And we've also identified evidence of active thrusting in the north beneath the urban area that's not visible in the InSAR. So there's great benefit to combining both techniques. Many thanks for listening. This is ongoing work, and any comments or questions are welcome.